Hello, this is Zheng. Please let me briefly introduce our poster titled Distinguishing Neural Signatures of Population Codes Encoding Uncertain Information, which is a joint work with Beck and Drugowitsch. There is ample evidence supporting that the brain can represent probability distributions. For instance, in Q combination, sensory information is combined proportionally to its reliability. Also, decision-making studies have revealed that decisions are shaped by prior information. And some recent work in reinforcement learning suggests that the brain represents full reward distributions instead of just expected reward values. Despite all this evidence, we still know very little about the exact representation of distribution in the brain. To get at those, let's look at a more specific example. Imagine we are training an animal to associate some odors to some reward distributions that follow the corresponding odors. Once learned, we may ask, how are the distributions represented in neural population activity? And in particular, what's the format of the representation? There exist several models that the brain might use for the representation of distributions in neural population activity. You might have heard about, for instance, PPC, probabilistic population codes, which is a popular one in probabilistic codes. Additionally, we have DDC, distributed distributional codes, and the quantile codes and expectile codes. While these models have already been proposed for quite a while, there's still no systematic comparison or evaluation done for them yet, partially because they are so expressive that it might be challenging to tell them apart in neural data. Regarding this problem, our main contributions are, first, we describe a set of properties which can provide qualitative differences between the codes, based on which we can make testable predictions. Second, we demonstrate how we can tell the codes apart from neural data by model comparison. Let me give you an example of some of the qualitative properties that we describe. We find that under PPC, if we linearly combine two distributions, say dA and dB, in the space of log odd to give rise to some new distributions, then the neural representation of the new distributions would be the linear combination of the neural representations RDA and RDB of the original distributions. This stands in contrast to the other codes, like DDC and quantile and expectile codes, where distributions need to be combined differently to give rise to the same linear relationship in neural population activity. In a word, the way of inducing linear combination of neural population activity can provide a way to uniquely characterize the type of codes. For a more data-driven approach, we wonder if we can tell the codes apart by model comparison. In a recovery study, we find that if we simulate the data in PPC, then we can always successfully recover PPC as the best fitting model. And for the other codes, similarly, we can successfully recover the type of the ground truth model. So at least in principle, code types can be identified from neural data by model comparison. In this recovery study, additionally, we find some properties that might be useful to support the experiment design. Finally, we carry out a model comparison to some data from mouse V1 in response to drifting grating stimuli. While multiple interpretations are possible, we find that interpreting the code as a PPC will give rise to the most recovered information. I hope you enjoyed this short introduction. To learn more, please come to our poster. Thank you.